Sir, for the assignment
Yes.
model checking assignment, what exactly you have to submit?
Ah, um, Zubin is here. Zubin, what is it that you want them to submit? Of course, you have to submit your
So
code with
instructions on how to use it. But I think that's
yeah,
all.
instructions on how to run, but a little bit more than that. Okay,
And
so the code has to have comments, or you should give half a page description of what the various parts of the code does. I mean, best I think is to put the comments in the code itself. That is one.
And if you submit the Jupyter notebook, right?
Submit what?
Jupyter notebook.
I didn't get it. What notebook?
Python
the
Jupyter notebook.
Python code.
the uh, IPython notebook. Yeah, you can do that also.
What is that? Python notebook, right?
The ones the way we were submitting the uh, SMT assignments. That if Tart was using the web interface where you can run Python code in cells and then
I see. Okay.
get the output below that.
Oh, so, but also, do you want them to submit? I've given some test examples that they should run on. You want the results separately? The output of
Or you can tell us how to describe how to encode formulas into your
no, but if they have
and
tested
check
it,
them with your.
if they have tested it, they can include their input and
Okay,
output.
I'll just describe how to use it and give an example of. Uh,
Yeah,
um,
that sounds fine.
No,
yeah.
no, I'm suggesting a little bit more than that. Since we are given a set of test cases, how about having you run on those test cases and then produce
Yeah, you can do
the
that also. So
inputs
yeah,
and the outcome, the results on those test cases?
yeah, that sounds good.
Because if each of you are using a slightly different kind of input, and that'll help you, Zubin, because
Yeah,
you want to test them on certain things. You may have certain additional examples and corner cases, etc., that you might want to test yourself to see what the gaps are and how well it is working and so on. Okay,
yeah,
but
okay.
nonetheless, certain minimum
Actually,
tests.
how are you going to test our code?
I'm assuming by running it.
Yeah, so you have your own test cases to run upon.
Additionally, I'm saying we will run it on your cases, on the test cases that I published on Moodle. That is, I hope you guys visit Moodle. And I even sent a message, I don't remember. So I have uploaded a file of test cases. You must, I don't know if you've reviewed it. If not, you go and then check it on Moodle. So what I'm suggesting is for you to produce the inputs corresponding to the test cases that I have uploaded along with the results that you provide along with your code. So we could actually run those again. And additionally, if Zubin wants to test on additional test cases, he will do that. That's what I'm suggesting. Is that clear? In addition to that, do you want anything else, Zubin?
No, I don't think so.
Yeah, so Zubin has to go today. So I guess not everyone is here despite my request. So that's all I can do. So Diganta, your roommate is here. I'm sorry,
Okay,
teammate.
so should we start or?
Yeah.
Who's that?
Yeah, me.
Oh,
Shomadev.
Who?
Shomadev, yeah, me.
Somadev. So that pair is here. And Kapil, your teammate is
Argadeep.
so that pair is here. Shivang,
Sorry, I was muted. I didn't.
Yeah, I'm pairing with Rishikesh.
Shivang, very clear. Yeah, I mean,
Rishikesh.
Rishikesh. Okay, 2 plus 2. Rishikesh is okay, so that's okay. So you at least one person is here. So that's fine. Okay, so we have 5 plus 2, 7. Good. So let me share and I will talk.
I have a question regarding the assignment. So we don't have to worry about SMTlib2 format for the input, right?
You're talking about the assignment, the CTL model checker?
Yeah. CTL model checking.
What about that?
So in the assignment, it's asked us to take inputs in SMTlib2 format, but what I have is just functions that take VDDs and input. And Zubin, I think, said that he had upload a parser, but
yeah, so I'll show you how to use the parser today, and
Okay,
I'll
okay.
upload
Today
it.
he will show you how to use the parser. If indeed you want to use that for that input. See, originally that is what we had suggested, but there were, a lot of questions, and I don't know, maybe each of you has done your own stuff. So that's why we're asking to give tell us how you do. I don't know, maybe everyone has, for this assignment, has his own way of inputting the formulas, I presume, correct? So yeah, so that is okay. Early on, we decided, no, you can do your own format, okay? So I had suggested to give a parser, but I don't know, there were lots of things, and I don't know how it is being done. So we want to make it more uniform moving forward for the SAT-based model checker project, okay? Now, are you suggesting something different, Zubin? Are you suggesting that they use the parser even for this because they've already coded? Now, I don't know if they will.
Yeah, so if they can want to, they can, because it'll be easier for us, and it's not that difficult to use the parser.
Yeah, but we should have done this long time ago. Okay.
Yeah, okay.
Now, I
Yeah,
don't
so
know.
it's up to them. So I'm saying.
Even now it's okay as long as you can describe how it is to be done. I have no clue how they are inputting right now.
Yeah.
Because if you do it today, then when the thing is it's due next Tuesday or something, So this is what is a mess.
So it's up to them. So if they want to use it, they can use it. But for the next one, they should use it.
So what?
Maybe you can start by showing what exactly the parser does.
Okay.
By exactly, I mean, what is the input, what is the output, and if they use it, how will they have to integrate, all the shebang, okay?
Yeah, okay.
Yeah.
So should I start or?
I think so. You start with that, and then I will talk about the project itself, what the tasks involved there are, and then you wait until if they have any questions about that, and then you can show some interface to Z3, etc. That's not questions about that.
Okay, so can you make me a co-host? Okay, so I'll upload this parser today. So the way its productions are, so it recognizes propositions which are variables, literals. So literals are of the form true or false, encoded like this. So you can use this or this. It has not, or, and, or, if, x, f, g, and u. So these are the things it recognizes. And
So I guess the literal has, in addition to true, false, prop also, correct?
yeah.
Yeah. Okay.
So literal is true and false, and prop is any variable. So
But usually literal is
so
defined
or
as not of either a proposition variable or a not of that. Okay. So that is how literal is defined. I mean, you seem to be defining it as true, false, constant. Huh?
yeah, it's only true or false for but so
Okay. The prop is just another.
or is
But that is, this is strange that the way that they have termed it, but that's okay. Because logically, when you say literal, it means the variable or negation of it. Okay, fine.
yeah. So so it does no the formula has to be unambiguous. You have to surround everything with parentheses, like any
That is infix notation.
yeah, it's infix notation, but you have to surround all infixes by parentheses. And the operators you can use are plus for or, a dot for and, bang for not, this caret for zor, and equal to for if. So these are the uh, binary operators you can use, and the CTL operators you can use are x, f, g, and u. So the way it works is you import it, and to parse something you call some is, so you have a formula encoded like this. So this is eventually and of AB. Dot stands for and. So to parse it, you call the parser.parse function, and uh, you will get the parse tree. So the way the parse you can interpret the parse tree is at the top level you can check its type. So you see that the top level thing element in this parse tree is an F, and it has a single child. So a dot child will give you another will give you the parse tree representing this and. So that has a left and a right. So you can do left, and you get a formula of type prop, and uh, uh, and if you look at it, it's an A. And if you do a right dot child, you get a B. And the type of the and is an and. So the way you'll uh, construct you'll consume this parse tree is something like this. So suppose you wanted to translate formulas containing only literals, not propositions, and not into uh, you wanted to translate a formula containing only the Boolean fragment of this without any CTL operators into a Z3 formula. So this is an example of how you would do that. So you would take the AST as input, then check if it's a literal.
So
And if
AST
it's a
is the
literal,
output of the parser, correct?
yeah, the AST is the output of the parser. And you would check if is it a literal. So if it's a literal, then you would uh, map true to the Python value true, false to the Python value false. Otherwise, if it's a proposition, you can make a variable. So the variable basically, yeah, so you make a variable uh, which for the formula. So the variable in this case is, if your proposition is something like A, then the variable this will output is the Z3 literal A with some number of primes denoting the level. So the level is not important here, but you might want to disambiguate an A that appears over here from an A that appears inside an X of
Is
A.
this for project?
Yeah.
Okay.
If you want to, you can use it for that. This also, but it's not required for your CTL thing. If you want to
But for
add a
project
parser to
also,
it.
we can choose whether to use parser or not, right?
No, for
No,
project it'll
I
be
think it's better that you
better
use
if
the
you.
parser there.
Yeah.
Okay. I mean, Kapil, don't get worried. Okay, this makes your life a lot easier. I'll tell you that, and all the way around. Okay.
So then you can check if it's a not, and
So
if the type is a
right
not.
now you have implemented some functions to take the AST and construct BDD, correct?
This is actually constructing the. It's constructing a Z3 formula.
So this is already doing the Z3 formula. This is for Z3. You have not done it for BDD, correct? So if they have to,
No.
yeah. So if they have to use it for the current assignment, they'll have to write similar things to convert to BDD.
Yeah.
I think, yeah. If you want to do it, you can do it. So that I think, but I think we should have given this thing earlier. Okay. But yeah. So
And otherwise, if it's
invoking the parser here.
So the parser will be invoked at the bottom somewhere. So you have a formula.
So these are functions that you have defined, and then you will do it. Okay, fine.
Yeah. So you feed it the input of the parser, and you can check the type of the AST. If it's a literal not or a proper or not, it has one child, so you can consume that child however you want. And if it is an and or an or a u, then it will have a left child and a right child. So you would recurse on the left child and you would recurse on the right child and construct the formula using whatever operation
What's an op map?
you wish. So the op map is maps the type and to the function and or to the Z3 function or.
Okay.
So it basically case splits on the type, right? So if the type is an and, this will be and of recur on left and recur on right. Otherwise, it'll be an or of this. So the parse is pretty easy to use. I'll upload it to Moodle today. So and note that you have to. So if you want to write A and B and C, you have to fully parenthesize your formula. So you have to do something like this. You can't do this. This is the parse error. So you have to parenthesize it fully. You can also do A and not B or C or something like that. So in this case, the type of A dot type of the right thing will be a not.
Right now, what does it translate F to?
So this function doesn't deal with CTL operators. It only deals with.
You just give an F. So
Yeah, I'm saying you can use when you actually do it, you can translate F to whatever you want. But I'm just telling you how to consume the parser, not how you should.
Can you tell how we can recognize the last operator that is applied in a formula? Like if the formula is AG, AF, P, then last operator applied is AG,
So
right?
sorry, G of sorry.
use CTL.
F of P, something like that.
Do AG or something.
G of F of P. There are two or more operators. The last operator applied is G, right? We will need this for generating the counter examples.
Okay, so
how do you extract the sub formula? Is that what you're asking?
Yeah, means the last used formula.
Last used formula.
Last use operator, something like that.
You walk down the abstract syntax tree and you can extract whatever that you want.
Sorry, yeah. So you can, yeah, so A dot, so the last formula would be the top level thing, right? So you just do A dot type and that's a J. Is that what you mean?
Yeah, yeah, okay.
So you have this, the tree
You have the partial.
and he is providing you all the functions to rip them apart. Okay.
So for this parser, can we just specify our custom grammar, or is the grammar fixed for the parser?
So I'll provide you the source code for the parser so you can change the grammar if you really want to, but I would prefer if you keep it in this form.
Yeah. So for CTL operators, you would want to have something like AF or EF or something like that, right? So what does just an F signify? That is why I wanted to ask.
Yeah, okay, yeah. So you can change that to AF and EF.
Right, okay.
And you have to also add two production rules for it. So change this P formula F into EF and EF. Okay, so I'll change this to reflect the CTL grammar before uploading it, okay? So you won't have to do any of this. So now we have AF and EF, and the parser should just work. Yeah. Okay.
But I was just curious whether the parser provides a general interface to specify the grammar or not.
So you have to change these production rules and then change the functions that recognize them.
Okay.
Yeah.
I guess I'll take a look at it.
So you wanted to change the input format, is it? The syntax.
So this one is for LTL, so I'll have to tweak it a little for CTL, the parser.
Why would it be any difficult? I mean, F replaced by
yeah, it's not very difficult, but
yeah, no, I was just wondering what what the interface for the grammar is inside the parser. So is it
this
something that
uses
is
the Python Yak thing for parser generators.
okay? I guess.
So I'll change the interface to CTL before.
I mean, I didn't understand the motivation for your question. So why would you want to change the grammar if you want your own, way of representing, providing the input as text? Correct?
No, yeah, I mean, I was just wondering what the interface for specifying the grammar for the parser is in general. Like I mean, I guess if we are given a parser for CTL, we won't need to change it, but in general, I'm just wondering that.
Because you might want to use it for something else.
Yeah, maybe. I just wanted, it seemed like an interesting thing.
Okay. So, should I discuss pushing and popping in the tree because I have to leave in 15-20?
You have to leave, is it? Okay. Okay. So I'll just give the context, yeah, okay. And then you can discuss. Just 5 minutes. I will give the context, yeah.
Yeah. Okay.
So they'll be able to understand. Okay, so same. One of the tasks I will after here. Zubin has to leave in 10 or 15 minutes, and therefore one thing I wanted him to show you before he left, And I'm trying to, I will be explaining why. And this aspect is something called incremental feature of SAT solvers. Okay. So given, see, one of the tasks that you will be doing for your project is implementing the bounded model checker. Okay. That's the for invariance, invariance property. And and for that, you know that you need to construct formulas of this kind. Okay. So you first construct is naught, where I is the initial state, and and you check if any bad state intersects with that. Okay. And you need to construct this formula and do a SAT check. After that, you have to keep constructing longer and longer paths from is naught. So you'll be constructing formulas of this kind, is naught and ts naught s1. That is k BMC k one long, and you will check if things. In general, you will be in the kth step. You will be constructing a formula of this kind. Okay. So if you have a path from S0 to Sk, which is represented by this formula, Ts naught S1 conjunction up to Sk plus 1, and you want to check that Ps naught is not true in any one of those things. Okay. So one thing is you can do every time you construct, I mean, you use a new solver instance to check these things. That is not, will be not as efficient as if you noticed each time that you are, for each k, you will be just adding one more, pretty much one more conjunct, and maybe you will be removing something else. So if you could put some kind of a checkpoint such that the SAT solver, if it has already solved, so done SAT check on some formula, and you're extending that formula, you're just modifying some part either by adding more conjunctions, or maybe you're removing some things, then you could, because the SAT solver does a lot of work in terms of generating all the conflict clauses and so on. And so you may want to preserve that. If the next formula you're just adding one more conjunct, all the conflict clauses that you've generated for solving a SAT instance up to, say, Sk minus 1, you can reuse them, okay? Because when you add something, a new conjunct, you are constraining it more. So all the conflict clauses that were derived for the earlier solver instance, they also hold good for these things, because if A implies B, C, A and B also implies C. So this BMC is one such case. I mean, typically for any kind of model checking application, when you repeatedly call SAT solver on in different formulas, and if between two SAT calls, the two formulas are only delta, they are different by a small amount, then you can use this feature of putting a checkpoint and then maybe modifying the formula a little bit, and then re-invoking the SAT solver, and then so that it reuses as much of the work that it did for doing the check in the last call. Now, what Zubin is going to, and you need to use that, and it's very easy to use, and you get, without that, the efficiency will not be very good, and also you're unnecessarily throwing off a lot of effort of SAT solving, and that's what Zubin is going to illustrate now, how to do that, and in your implementation in the SAT project, you will have to use that feature. Okay?
Okay. What you want to do is you want to assert some formulas and then slightly modify or add a few more assertions, but somehow roll back to the previous state you were before you added those assertions. So suppose you have something like declare const x, you have one integer and you say assert x is greater than 0, and then you can check that and you can get a model and it says okay, x is 1. So now suppose you want to add some new constraints that aren't permanent, that you might want to roll back someday. So you can so the way the method Z3 provides is you can do a push command. So in Python also it looks similar. So I'll show you the Python later, but it's basically solver.push to enter a new stack frame. So you can have, so x is still 1 if you get the model. Sorry, check that. Get model. You see x is still 1, it's still in scope, but if you can add new constraints, you can say something like assert x is greater than 10 at this point. And then you can check that and get model, and you see okay, x has changed to 11 now. But supposing you don't find or you can add something like, you can make it unsat by adding something like assert x is less than 6, and then when you check that you get unsat. But now suppose you want to undo all of this stuff since you last pushed. So the push is here and now you want to undo all of this. So what you say is a pop. Now what this does is it rolls back to the state to just before the push. So if I get if I check sat here, I get sat, and if I get model again, you see the model is 11. So earlier the model we had was 1, but you can see the sat solver is somehow not throwing away its work. So by here, when it computed a new model for this assertion, it computed 11. So when you roll back, when you pop here and then you get the model again, it knows that this x is greater than 10 is consistent with x is greater than 0. So these two things don't conflict. So it can keep whatever work it had done at this point and it doesn't need to throw it away. So it keeps the earlier model that it had, 11. And it's still, because 11 is still greater than 0. But at this point, you can add new constraints like x is less than 5. And then check sat. And this is sat again, because the only two constraints that we have on x right now are x is less than 5 and x is greater than 0. And if you get model, you'll get 4. And you can another point is you can enter multiple layers of pushing and popping. So I'll show you how to do this in Python now. So you import Z3 and you say something like yeah. So let's say x is Z3 is an integer and you want a solver. So s equals solver. Sorry. Yeah. So now you can s dot add x is greater than 4. Then you can do s dot push, s dot add x is less than 10, s dot check, s dot, and you see x is 5 at this point. And then you can push again. So you can push multiple times. So if I push here and I add something like x is s dot add x is greater than 11, and then I check, it'll say unsat. But I can roll back this by doing a s dot pop.
So
now,
pop would roll back to
so-
the last push.
Yeah, so
to roll
to
back
this
x equal to
add,
5.
yeah. So we have over here we have x equals 5, and the constraints we have are x is greater than 4 and x is less than 10. So the last push is this one. So these ones are removed. So x is greater than 11 is removed. So I can do an s dot check over here, and s dot model is 5 again. So it's the same model we had over here. Yeah, and now so if I because we did another push earlier, we can pop that one too, and we can add something that conflicts with this, but we'll still get a satisfying instance. So we can add something like x is greater than 100 and s dot check is sat, because we popped this one away also, because we did two pops. First pop removed these constraints, and the second one removed these constraints. So if we get a model, we have x is 101. So this is how you can use this feature for Z3. Any questions? No, I think it's clear.
Okay, so you've already shown them how to use the interface. Has that there is Z3 APIs. Okay, so
Yeah.
not done any assignment on that required them to use the Z3 API, correct?
No, we did give some questions in the first assignment. We gave two questions. One was just a simple logic puzzle, who murdered who or who is guilty, that kind of thing. And the second one was a transition system that they had to model in Z3.
Yeah, but that they could do. So you guys did that using Z3 API. So you're familiar with Z3 API usage to embed these APIs inside the program, correct? Guys?
Yeah.
Okay.
Yeah.
Yeah. So because here in this assignment, in this project, you will be building like a bounded model checker, which means that you will be generating, given a transition system and a property to check, you will be generating formulas, incrementally longer and longer formulas, and you will be invoking SAT solvers for this incrementally longer and longer formulas repeatedly.
Excuse me if I'm wrong, but we have seen only model checking of AG, right? Not other formulas.
That is correct. What you have done is this bounded model checker, you've only seen it for safety property in simple like G and F, correct? That's what you mean, yeah?
Yes.
Yeah. So I will go through the exact tasks involved. There's only one component there for which the material I have not covered. One of the tasks for which for which I have not yet covered, and that I will cover in the partly today if I have time, and if not next class. After that, so that it will be clear. All the rest have already been covered, like the BMC and the K-induction, so that you can get started. Okay, right away. Correct. Yeah. So my thing was, since Zubin had to leave, so if you had any questions, I mean, he'll be available later also. This is something that I thought that you must know before you start implementing on the first task of the next project. Yeah. So if you don't have any questions for Zubin, I will allow him to take leave.
I just wanted to like ask something about the current assignment. So like using some other parser right now, third-party parser is fine, right? Even if we haven't written a parser on our own.
Yeah, for the CTL thing, it's fine for the model checker.
Yeah.
Uh, yeah, you can do it in any input format as long as you describe how we actually input.
Yeah.
But was your question about, if you could use your own parser even for the next project?
No. I was just wondering if using some third-party parser for this project was like this assignment was okay.
For the SAT solver project, if that was okay.
No, for the current one, I've used a third-party one.
For the BDD one.
The BDD one.
Oh, okay.
Yeah.
That's okay. That's fine. So we're not insisting on it.
I also have a question about counterexample generation for general CTL formula. So suppose we have a formula like AF of something or AG of something. So in that case, a counterexample will be.
I will take the question. So do you have any specific questions regarding what for Zubin, what he introduced? So because he has to leave.
No. This is not particular.
Okay. So Zubin, if you want to leave, you can leave, or you can hang around however long that you want.
Okay. Yeah, I might stay for 5 minutes.
Yeah. Okay. Fine. So what is your question, Arvadi?
So if we are given the general CTL formula, so suppose it is like AF of P or AG of say Q, then a counterexample for that will be a counterexample for AF of P and a counterexample for AG of Q.
Yeah. So you're proposing. See that I said. I mean, it'd be interesting if you could figure out. That's why yeah. So you were suggesting how you could do that for nested CTL formula.
No. This is not nested. This is like one formula and a conjunction, disjunction with another formula or a conjunction.
Ah, okay.
So in that case, we have to counter both of those formulas if it's a conjunction or at least one of those.
Correct. Yeah. At that level, yes. I mean, you can separately generate, right?
Yeah.
Something that either if it's a conjunction, both of them has to satisfy, and therefore the example. Yeah. No, but if for conjunction and disjunctions, it is at one level, it is kind of easy to handle. I mean, if you want a counter example, you have to show that it's a disjunction, that it is for both. Yes. As
so
long
we just
as
generate multiple counterexamples.
correct, you can have two different counter examples.
Is it even a CTL formula, like end of two CTL formulas?
Yeah. What about that? What is your question?
Is it even a CTL formula? Like say AG of P and EG of P.
Yeah, that is a CTL formula, because two you can take conjunction of state formulas. That's fine. What you cannot do is E of F and AG kind of a thing. Okay, those kinds of things you cannot you cannot do.
So even if the top level is a Boolean connective, and if we have lower levels that are not a Boolean connectives, even then generating a counterexample is, I mean, it doesn't, like, I don't see.
I'm not requiring you to do that. Okay, so this was.
Yeah, but like I'm just. Yeah.
Yeah, I was just thinking, since Argadeep is asked that question. So
in
yes, if it's AG of something and thing, it is just a conjunction of two state formulas. Therefore, for that to be true, if that is not true, then either one is false, correct?
Yeah.
What you're saying is you will show a witness to whichever is false. Yeah. Now, I had not clearly specified that I'm okay even if you did not do those kinds of conjunctions, yeah, of things. I'm happy. But if you want to do it, for any CTL formulas, because I had stated it as CTL formulas, then the question of, so your model checker already does take care of these kinds of conjunction, of legal conjunction of CTL formulas, correct? That's why you're asking this question, Argadeep?
No, it doesn't actually. It just, I mean, I can make it do it by explicitly writing a formula.
No, but so the question you're asking is of general interest.
No, I was wondering how it would play if we were to use a parser. Since right now what I have is just functions like EU, I mean a function for AG, a function for AF.
Yeah, but you do support nested formulas, correct?
Yeah. But in that case, the argument will be just a
Your question
BDD.
was
That
with respect to parser or with respect to, now I'm confused. So if you were to give conjunction of state formulas, each of which is in its own right is a CTL formula, how do you parse it is your question? How do you check it is your question? How do you generate?
no. How do I generate a counterexample?
Specifically with respect to counterexample, you're asking that question not with the intention of implementing it, but just as a
No.
general.
Yeah.
Yeah, I mean, I guess that's what it would, it would be. If it is false, then you would have to generate a witness to whichever part that is false. Why? In any explanation that it is false, of why it is false as a witness is what you need. Of course, just producing a state which makes it false itself is, technically a counterexample. But since each of them is a CTL formula, a more meaningful explanation would be why neither of, if it's a disjunction, why both of them is going to be false. I guess you could define it like that. Yeah.
In that case, there could be two different paths that make.
Correct. There'll be two different paths.
Yeah, then you have to generate multiple counterexamples.
Multiple counterexamples. Correct.
So if we have something like, say, multiple levels of Boolean connectives, like something like some CTL formula or some CTL formula, and then that whole thing ended with some other CTL formula. So in that case, how would we, like, what sort of counterexamples would we have to generate for that? That is what I was.
Yeah. So this is if you nest such formulas inside other CTL formulas, you're asking, right?
I mean, if you have multiple nested levels of Boolean connectives at the top level, like say AND of odd of some CTL formulas or something like that.
Yeah, but that is kind of, you can extend this, what you just now described, to those levels. No? So you have to generate for every for every unsatisfying instance, if you want to generate separate path formulas that violate each of them, then there'll be quite a few of them, isn't it?
Yeah. So I mean that seems like listing out the satisfying instances of a Boolean formula, which does not seem like.
No, but I mean that itself you can do, okay, by making each of them propositional formulas. But if you want to, ideally, I think, I mean, generating one unsatisfying, I mean, if it is not true, if it is not valid, okay, and then you pick one, satisfying. I mean, you take the negation and you have to find a satisfying instance of that. So for one, you could probably generate. Huh?
Yeah. So we'll have to basically sort of do something like a SAT model generation step and then follow that with actual.
And then follow that up with one of the things. Yes.
Yeah. Testing
did any of
CTL.
you check what new SMV does for nested formulas? Okay, this extension to Boolean combinations of these things is not that hard. Okay, although I mean, it gets complicated, something that you will have to do. But for nested formulas, what exactly is meaningful is something that is not clear to me, except for generating up to a first level. Okay, and if the nested level is a E kind of a formula, then you can generate a witness. But when it flips it to an AG formula, I really don't know. I was not able to give you a conclusive answer. So I wanted you to, as an exercise, just to go to new SMV, type it up, and then see what it does. Okay, I would still want you to do it. Okay, just for information's sake, and then see what it does. Okay, and illuminate the rest of us. Can you guys do it and check in USMV what it does? Do a like an F of G, like AF of AG or something.
Yeah, okay. I'll do something like that and check.
Or EAG. I mean, infinitely often do that because that is representable in CTL. Yeah.
Yeah, I'll check that and see what new SMP gives.
And just for information sake, that's all, because that is not part of the assignment as we decided. Yeah. Yeah, here are some other interesting things, that just came to my mind. Okay, and I'm not saying, I mean, I'm not insisting that you should implement this. I'm not asking you to implement it. But these are some questions that you could see if you can come up with some solution on your own, and maybe, who knows, this might I may decide to have one of these questions on your final exam as well, because they are interesting in their own thing. You remember that on the fly version of model checking that you had, where you could prematurely terminate with some conclusion of whether you have found a bug. Usually, I mean, the one that I illustrated was I'm talking about the first question here. Let me maybe bring it up. The slide. I don't know if I have it. I've forgotten which. Maybe it is this one. This is the one. Yeah.
So in this project, we don't have to do interpolation, right?
No, I have not even come to that project yet. Okay, so if you want me to go to the project, I will do that. So hold your questions. So maybe I will go through that. That's far more important, before finish. Okay, so I come to this if I question. So here is the tasks for the project. So by this project you mean the next one, correct? The team project, correct?
Yes, yes, yes.
Yeah, I haven't included the interpolation thing, okay, because I don't think you have interpolator. But here's what I'm having you do it. First task is to implement the basic version of BMC.
So the
Which,
screen is not visible. The screen is not visible.
I'm not sharing it, is it? Okay. Oh, so far, it's not even sharing it. That's stupid of me. By basic BMC, what I mean is doing this. Remember that, so you assume that you have as input the transition relation, initial predicate, and a predicate P that you have to prove. As an invariant or an FP or a GP kind of thing. The P is a predicate. And we've already decided how to input, etc. the parser. So what it has to do is to generate BMCK formula for for any given K. Then you basically have to implement and check by a BMC formula. I mean, it is a formula whose satisfiability reveals the presence of a bug for up to K length, K long, okay? And that should be embedded inside the BMC loop. And you can assume that you are given a particular threshold, and you just has to incrementally check longer and longer BMC formula for presence of any bug, K long bug, up to that given threshold. Okay, so that is what this one was, if I may. So many slides. This one. Yeah, you'll be implementing these, generating formulas for that, and then doing this, okay? We'll exactly implementing this loop as the first task. I mean, you won't be taking a C program, but you will be just reading the transition relation, initial predicate, and a property predicate, okay? So that's what you will be implementing. So then the second component is you will be implementing, computing the reoccurrence diameter for any given T as a SAT instance problem, so that you can use that with your task one to do it. That is exactly doing this one. This one. So this is also a simple loop given a T and a thing. For longer and longer thing, you will find the smallest D through repeated SAT checks. Okay, what the for a given T, okay, for a given transition relation, you will generate formulas, for this and check threshold. Then you will implement the K-induction loop to check a given safety property. Once you have done this, these two are different. The number two is kind of different. Once you have done the basic BMC-K, doing K-induction is fairly easy because some part of that is done. And the only inductiveness check, you will be generating a similar BMC formula and then slightly different, but a similar one. And that is exactly implementing this loop, this one. And you see, the first task, you've already done this part, and all you have to do in this case is the second part, which is only a slight variation of how you generate the formula, and you implement this loop, okay? So inside this loop, you will be making, this is just like a BMC loop. There you will go up to K, whereas here you will be checking two things, and there'll be a termination check. If you get a counter example, you will terminate, or if you perform this check, and this validity will be turned into an unsat, and then that passes, then you will generate verify. So inside here, when you iterate for the next iteration of the loop, you will have to do some push and pop, like what Zubin illustrated. So you will be adding a few constraints, and maybe you will be removing something. So that's what you have to figure out. So for each step, you will have to give a checkpoint. And that's what I mean. The star I've shown here are where you create your checkpoints, okay, using push. And then before you do the next iteration, you will pop up to that previous star and do it. That's just a matter of small matter of detail. And then the fourth part is extending what Kapil asked. Okay, the first part here is only for G and F, GP and FP. So I will discuss how that bounded model checking can be extended to arbitrary LTL formulas. And with some restrictions, I will have you implement for some subset this extending it to certain arbitrary formulas. Once again, the bounded model checking model checking part. Okay, this I will discuss in the next class, the number 4. Now, what I want you to do is, this is, 2-person can share the load. So right in the beginning, you will have to, since 1 and 3, 3 is very much built on top of 1, okay? You could, so you will have to sit down with your teammate and forget about all these site-in transformations. None of this is required, okay? So, I haven't even discussed this in class. So you could just use the kind of the code that Zubin showed to directly get the formula and so on. So going back, you will have to sit down and see how you distribute the work, how you could maybe start, while your teammate is doing this BMCK, you can actually start thinking the other person can be doing this, number 2, which is of a different kind, and have a scheme, for K induction with holes in that, so you'll have to do some parallel activity. And if you plan it very well, I think this is certainly doable, and it will be a good learning experience as well. Okay, so you will have to involve your partner fully, each of you, to get it done. Yeah, if you have to think about this problem. So, and also I'm wondering if I should have some intermediate deadlines, okay, so that you will not push it. Okay.
Sir, how we can handle nested formulas here?
That I will discuss as part of 4. Okay.
Okay. So for the first part, we just need to check for the property in AG, right?
Correct, with the predicate, yes.
Only AG is fine.
No. Well, it's not AG. Don't think in terms of, these are all now in terms of LTL. See,
Okay.
when you only have one level, AG or AF, it is the same, G of P and F of P, okay? And this part, the extending nested part, will be done for LTL formulas here, okay?
Okay.
And that's why I wanted, since you've already done CTL, you will not be just doing the same CTL in SAT. No, you will be doing bounded model checking of LTL formulas, okay? For the first part, and that is where the nesting comes into play. That I will give you a little bit of indication now, okay? I mean, I will just give you a teaser today, and on next Tuesday, I will discuss it completely as to how you can generate these formulas for arbitrary nested LTL formulas. After that, the checking is just, you will have to implement the generation part. That will be just like BMC for different nested formulas. After that, you just send it off to SAT, and that's it. Okay, so it's only the generation part that it will be that you will have to do, and then I will check, and that is based on some thing called bounded semantics for LTL, which I will discuss next Tuesday. And since we still have 5 minutes, if you don't have any other high-level questions, I will give you a teaser of how you extend that to arbitrary LTL formulas. So what I was saying was, so that you guys will not, kind of defer everything to the end and then get tensed up. I thought I will have one deadline for 1, another maybe deadline for 3, okay, and finally for 4. So that just to keep you honest and keep moving. Is that reasonable? Okay. So since at least some of the team members are here, you think you can work with your team members so that you will truly share the load. Otherwise, this can be a little bit too much for one person. So you have to make sure of that, okay? That you plan ahead and that you will do. And the only thing that is, I think, not exactly, maybe the number 2 might not be as clear. I will discuss that if you have any doubts for converting the computation of the reoccurrence diameter in the SAT instance problem. I can clarify the doubt there. This will be like a loop in which you will be checking somewhat of a similar thing repeatedly using SAT. Okay, so if you don't have any questions, just 5 minutes, I will. Yeah, so what is bounded satisfaction? See, this is all for LTL formula. So you have to switch your mindset a little bit, and then, so, but in this one, yeah, so it's for LTL formulas. LTL formulas are, unlike CTL formulas, which are the satisfying things, objects are states. LTL formulas, the satisfaction relation is for paths, infinite paths, right? So LTL formal semantics is defined for every LTL formula, what it needs for a particular infinite path to satisfy that formula. So here, so we are defining something called a bounded satisfaction. So you say that a formula phi satisfies an infinite path pi with bound k if the satisfaction of the formula phi on the infinite path pi can be inferred by inspecting only a k-long prefix, okay, of that path. Okay, so that's how it is defined. Okay, so given that definition, I will ask this a question. So first take the first one. So I will give a formal definition of what bounded LTL semantics is in the next class. So now I ask you a question. Suppose an LTL formula, just a predicate is certainly an atomic LTL formula. If you want to check P for, if it is true for a path pi, by looking only at a k-long prefix of it, what is the prefix that you require to check it? You understand the definition of bounded semantics? So when does a path satisfy P?
We look at the current state, right?
Correct. So if you're given a path like pi is equal to pi s1, s2, etc., by just looking at the first state, you can tell, correct? So for k is equal to 1. So you only need to look at a prefix of that path pi, one long thing, yeah? So then we say P, for P, it is, formula. Of course, it depends on the, this value of k will depend on the formula, the structure of the formula. If the LTL formula is just atomic predicate P, then you're right, okay? So k is 1 because you can check if it is true of the first prefix, which contains only the first state, and you can tell. How about for x of P?
2.
Correct. So for k is equal to 1, you won't be able to tell. Okay. So if by looking just at the prefix of length 1, you won't be able to tell. Similarly, for x of P, what is it? Hello?
3.
Yeah, well, it's actually not the, yeah, it's xp is 2. This is 3, you would think. So similarly for x to the power of I, you would think it is I,
I
right?
plus 1, right?
Huh?
I plus 1.
I plus 1. Okay, fine. But that's what you would think. But it depends. Here's what I'm saying. What if this thing is, say, if the path is such that it is a self loop path, then S2 is equal to S1. Okay? So if you had information of whether the path is lassos, so in this case, I'm saying if S2 were equal to S1, then the K that you need for x to the I of P is just 1, correct? So, or if it is something like this, yeah, dot, 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 then you go S, L, okay, with SK is equal to SL. So that's what I mean by path lassoing, okay? So if this, in general, if it is something like this, then if you have that information, that if it is a lassoing path or not, then you could, and depending upon where it lassos into, you can actually, yeah. So for this, it is maybe x to the, of course, x to the I, if it is, if I is less than or equal to L up to L, it is this. So up to K, you might have to do for I greater than or equal to K, okay? Since if you know that it lassos into SL, then K itself is the bound for x to the I of K, correct? Okay, because you know that it lassos with SL. So if you had that information, because if you know that the path is indeed lassoing, if there is no lasso up to K, then you won't be able to say anything for x to the I of P if I is greater than K. Okay, up to K, you will be able to tell. But if I happens to be greater than K, then you can't tell in general for a non-lasso path. But if it is a lasso path, which you can actually check using SAT, then you can, K bound is good enough for you to check the satisfaction for the infinite version of this path, okay, which is where the states from SL to SK keep repeating, okay, but that path, because that is the path that this one, the infinite path, this represents, okay. So if if you could use that information as well in your check, then you could actually find a bound on K up to which you need to check to do that, and that is the idea that is used even in the BMC formula. Okay, so the basis for generation of the BMC formula was this. Okay, so it was actually this. The basis was this bounded LTL semantics. Normally, standard LTL semantics is defined for infinite paths. Now here, you define what it means to infer the satisfaction of of a particular formula on an infinite path by only looking at finite prefix of it. Okay. Now, let me end by just asking you to see if you could answer these questions. So for GP, for what K? Can you ever check the satisfaction of GP for any? We're looking at only a finite prefix of the path.
It can be at most the number of states, maybe.
No, but that is the bound. Okay, I'm not talking about. So check for a given path. I give you a path. I've given you a path pi. Okay, and I've also told you, you could use the information of whether it is a lassoing path or not lassoing path. Given that, give me the answer. I'm asking you to. I'm not asking you. Yeah, K is the bound. Up to that is a threshold bound, etc., etc. That I understand. But what I'm saying is, given a particular path, which is an infinite path, if suppose it were lassoing, suppose it was lassoing after K, like here, isn't it enough to check that P holds good in S1, S2, S3, all the way up to K? After that, and then you have to check if it is indeed a lasso. If the path is indeed a lasso, then you only need to check if P is true up to SK for that path, okay? It's only I'm asking you for that particular path. All the threshold bound, etc., that we defined was for the entire transition system, for all paths that are possible, execution paths that are possible for the transition system. We'll have to get to that if you want to check it for the entire transition system. Right now, I'm asking you the question with respect to a particular path. Okay? If the particular path is indeed a lasso path, then you have to check if P is true up to SK. Otherwise, if it hasn't lassoed, then you cannot conclude whether GP is satisfied or not. So because if every state from S1 to SK are distinct, then you don't know, okay? By just looking at that prefix, you won't be able to check, say conclusively that GP is true for that path. But if it was a lasso, if the path is lassoing from SK to SL, then just checking for every state from S1 to SL, if P is true, is from that you can conclude that it is satisfied for the entire infinite paths. Okay, that is how you will generate. Now here, how about this for FP? So for GP, if it is non-lassoing, you cannot conclude anything. Okay, but if you know that it is lassoing, then all you need to do is to check for up to the point K where it lassos. Now, I ask the same question for FP.
Will it be the same thing? As in, we don't have to check up to the...
Yeah, just think by splitting the answer to the question on two cases.
Yeah.
Suppose it is a non-lassoing path.
Yeah, then P can happen as late as possible, so we don't know how long we need to check.
But what if it happens? If for a particular path, if P is true in either S1, S2 up to SK or SK, if that happens to be true, then you know that any extensions to that path is FP is true of. Okay, but if so, you can give some partial thing here, unlike in GP, where you cannot conclude anything by looking at a K prefix, a finite prefix, whereas here, if P happens to be true in one of the states in the finite prefix, then you can conclude that by just looking at the finite prefix that it is true for the entire path. Furthermore, if you know it is a lassoing path, And if P is never true, that it is never true up to, in any of the states up to K, then you know that it can never be true for the infinite version of that path. Okay, so having the information whether it lassos or not, you can actually do more. I mean, yeah, so you can do this. So that is the idea of the bounded model checking was for that case. Okay, so it was actually derived, the basis for the derivation of the formula that you use for doing bounded model checking was just a special case of this. It uses this general bounded LTL semantics. Okay, and that's what we will look at. We'll first look at bounded LTL semantics. Based on that, how you generate a formula, K-long formula, K-long BMC formula, whose checking you can conclude some information about the satisfaction of the on paths, and then extend that to checking for all paths for execution path generated by a transition systems. And we will see that this will be a natural extension. I introduced BMC as a special case, and you will see that this is the real basis for the bounded model checking approach. Okay, so that's what we do. So I'll end here. Okay, if there are any quick questions, I'll take. Otherwise, I'll see you next week. Yeah. So any questions?
So even for GP, we can sort of say that, like, if P is not true up to some length K, then I mean whatever the extension is, that it is not true, right? So that's sort of a partial answer we can also provide for GP, right?
Yeah, I mean, as a violation, probably you can check, okay? But whether it satisfies, you can't check. Yeah, I mixed the two things up, okay? So I should not have done that, okay? Although the way that BMC is used as a violation, here I'm asking the satisfaction problem. Whereas as a satisfaction problem, you cannot conclude anything for GP. But as a satisfaction problem, you can conclude for FP. Because if P is true in any one of the first SK states, and additionally you know that SK state lassos back into SL, then you can conclusively say that FP is satisfied for that path pi, okay? Which is what you cannot do for GP. Violation, yes, okay? You can conclude, but I'm posing this as a satisfaction. So as a violation, you can definitely check the GP by looking at finite things. Whereas for satisfaction, by looking at only a finite frequency, you'll never be able to tell GP is true. Because even if P is true all the way up to K, you can't tell anything, correct? Yeah.
Right. Yeah.
Violation, you'll be able to. Whereas the violation will require you to check for lassoness, for FP. Okay? So that is the what do you call it? The duality. Yeah. So since I was posing as a satisfaction problem, the answer is no for GP.
Right.
We can take double negation, right?
What?
You can take double negation and put the formula as negation of f of negation of P. Then that will be a satisfying problem and the condition will also hold.
I don't think you can do it for LTL. You can do it for CTL.
No. See, if you take double negation does not do
True.
I mean, double negation for what? That is the question. See, that's why what this is really used is, although posing is a satisfaction problem that is useful for generating the formulas, it is, if you want to check, you can only use it for checking in the negated fashion as witnesses, because SAT is witness, it produces a witness. Therefore, it will be used, as you will see, as you take the negation and check if there is no bugs, and then you keep extending that to up to a certain bound where you can then conclude. See, if you want to do it for all paths, you will have to take the negation. Okay, so I guess if you take, I mean, I want to understand what exactly you mean. I mean, who's the person who asked this double negation thing? So,
Shomadev, yeah.
now, you know, I want to understand the question. So I don't fully understand. It's getting late. Okay, so we can revisit that. So double negation, if your thing was you can take double negation and reduce it to satisfaction, you know, but if you take double negation, you get back GP, you know. So I don't know what that means. If you take double negation of GP, you will get back to GP. So you're there where you started. Okay.
That's the whole point, right?
Yeah. So that's why you can't do it. If that's the point that you're making? Yes, correct. Yeah. But you will see the way that this will be used is by taking the negation and then showing if there is a witness to violation. Okay. Because that's, you know, these bounded semantics, if you want to use it for some verification, you will have to use it by taking the negation and checking if it is producing a counterexample, and then you run it up to a certain K. Okay, and how do you find that bound is what is the catch. Yeah. So like Kapil said, you know, yes, you could do kind of, well, yeah, I mean, I don't know. I mean, I want to understand what Kapil said as well. So I think that CTL, you can do that for state. Yeah, I didn't quite understand, you know, what he meant. But anyway, it's getting late. So let's end it here. We'll take it off. Okay, this is what we'll do. And we will discuss completely the semantics, the bounded semantics. It's quite interesting. And there is a similar version for CTL also that we're not going to cover in this class. For LTL, we'll cover, and then how to make it complete is what we will cover. That is one approach that is used as the SAT approach, and then there is the other approach for LTL. And that will be the end of all the technical portion of this course. Okay. So, and what you will be doing as part of the project is generating the bounded version for arbitrary LTL. I still haven't not told you how to define this for arbitrarily nested LTL formula, which I will do, okay, next time. Okay, see you next time. Thank you.